Val, when we look at models of the globe, we often look at it so that the poles are kind of almost hidden away at the top and the bottom, and yet they're very, very important. Tell me about how satellites are used to sense in those areas.
Well, this one we're looking at here is the current state of the ocean seen in sea ice and sea surface temperature. And as you can see, it looks like it's breathing really fast, but it's the seasonal cycle, and you can see the Antarctic sea ice shrinking and in the summer and then expanding in the winter.
So this is a whole year that's condensed into just a few seconds?
It's actually about 10 years condensed.
There are particular challenges to getting satellite data over the Arctic and the Antarctic. Tell me about those.
One of the things is high latitudes are covered by polar orbiting satellites, and it's actually very difficult to get those satellites to go really close to the pole. Mostly they don't go far enough, so you get a big hole in the middle over each pole. So if you want to measure something like sea ice, for example, or Antarctic land ice, then you need to go much closer to the pole. And the closest anybody's gone so far with satellites is a satellite called CryoSat. And that went so that there was a tiny, tiny little hole left. But you cannot go right over the pole. If you want the Earth to be covered as a whole Earth, then you have to go a few degrees from the pole.
So the idea is that if we have a sphere here, for example, you think about if the poles are at the top and the bottom, we think about polar orbital satellites perhaps as going over the top, but they're not doing that. They're going slightly to the side. And because they go slightly to the side, their orbit goes around. So each time they draw a different line.
Yes, so it's actually not the orbit. The orbit stays in the same place, but the Earth goes around underneath the orbit.
So you can colour in a planet as long as you're off slightly away from the poles. So that creates a problem if you want to know what's happening at the poles.
Yes, so if you have sensors that look to the side, you can get close to the poles by looking sideways. But CryoSat had to look straight down to measure the thickness of sea ice, which meant that it needed, and the thickness of land ice, which is looking straight down, and that meant that it had to get as close as possible, because otherwise would have a gap in the middle. Now the gap in the middle in some ways is where there's least variations in the ice. So it's not so difficult, such a problem that you can't measure it. What we wanted to measure was the ice margins, and CryoSat had very high resolution altimeter, so it made it possible to measure the ice margins, the edges of the land ice and the margins of the sea ice, and it got very close to the North Pole. So there's only a little hole in the middle where it couldn't measure.
So ice looks very simple when you look down from above because it looks just like a white block, but actually you've got ice on land, ice on the sea, you've got icebergs and sea ice, and the sea ice can have different thicknesses. There's a whole load of new things you want to know about once you have ice. What can a satellite help you with?
The first satellites that looked at ice were microwave radiometers, and they measured just the temperature and they got the ice. They got quite good distinction between ice and open water, and those are the ones that actually told us that there was a real problem in the Arctic, that Arctic summer sea ice was shrinking really fast.
So the first game is just how much ice does the ocean cover?
Yeah, and how does it change, and how much does it shrink and does it recover? And we discovered that it was shrinking much faster than we expected, and that the Arctic was likely to be ice-free, in not too distant future. But then comes the thing that you want to predict what the ice is doing. You want to predict that both from the future climate point of view, how fast this is shrinking, but you also need to be able to tell people where is ice that could be a danger to shipping, for example. So those models need to know how thick the ice is, and it needs to know where the ice is broken up and where it is solid. And that was difficult because the microwave satellites have got a really huge footprint and they averaged over a very large area. The conventional altimeters could measure ice as well, but they measured over a large area, so they didn't pick up all the gaps in the ice. They couldn't really measure ice thickness very well. And so we had the new satellite CryoSat that is still up there measuring ice. And that was actually because it had much higher resolution and a new type of altimeter, which is now all altimeters is going to be like that. But that new altimeter could measure the margins of the ice sheets where we knew that all the changes were happening. What changed there we could not measure until that satellite went up.
And these are very inaccessible regions. It took humans a long time to get to the North Pole just because it's bumpy. It's not like land where you could just go over spiky mountains. It's changing and it's shifting, and you really need satellites to get there. And
making measurements there is really expensive, sometimes almost impossible. And so the only measurements we made a lot of measurements as part of the campaign to validate the satellite data. So there was a lot of polar expeditions to do that. But once that has been validated, we know the effect of the snow cover on the ice. We know how to calculate the ice thickness from that data. And once that's been established with the ground measurements, then you can rely on the satellite data to carry on measuring. And it monitors in a completely different way you could not do with people pulling a sleigh.
And tell me, we're looking at the Antarctic here, but the Arctic is a region that's changing very rapidly at the moment. And it doesn't just matter, it's not as though more ice or less ice is just, oh, more ice or less ice. That affects other things like currents and ecology.
Yes.
Tell me about those other
Yes.
consequences.
The ecology of the Arctic is completely dependent on the big story is the polar bears. They need sea ice to live. Their lean time is in the summer. If the summer sea ice disappears, they have nowhere to go and fish. And there are a lot of other things that rely on the ice as well. So the whole ecosystem is centered around the balance between ice and ocean in the Arctic. In the Antarctic, there's not that much change to the sea ice at the moment, so that's not the big thing. But in the Arctic, it's a really big problem. And of course, once you open up the shipping routes across the Arctic, that will be quite much quicker to get across from one part of the world to the other. But that has its own problems because that will bring with it things like oil pollution and drilling and so on. But the whole polar ecosystem, the whole Arctic ecosystem is centered around ice. And when the ice disappears, there will be a really big upheaval and big changes.
So we're watching the changes in ice and we're learning about some of the changes to ecology. But also when you add or remove ice, you're also affecting the flow of water underneath.
Now that is mostly the land ice because the flow of water changes to that works on quite a long time scale. And when the sea ice melts, okay, so the water gets fresh in the surface, but it doesn't have a big impact on the ocean circulation. But a very rapid melting of land ice could do that. And in fact, in the past, we know that about 8,000 years ago, there was what we know now called the 8.2 kiloyear event. And that was actually a rapid melting. It was the melting of the American ice sheet, and there was a big lake that suddenly broke through the ice barrier and flooded the Atlantic, and the temperature in Europe dropped by about 4 degrees over a very short period and took over 100 years to recover. And that's one of the things that worries us now, that the changes as ice melts and as you get more rainfall over land and more river flow into the North Atlantic, the thermohaline circulation will slow down, and that's what drives the ocean transport of heat to high latitudes. And so, although there's global warming, Western Europe might actually cool down, or at least not warm very fast. And we are monitoring that.
And the sort of monitoring of sea ice you can do with satellites also matters because sea ice is very reflective,
Yes.
but the water is very unreflective.
Yes, that's part of the Arctic amplification. Summer is the time when the sun really heats the Arctic. And if there was ice there, most of that light would be reflected back up. But with no ice, then all of that water will be absorbed by the ocean, and it's very dark, so most of that heat will go. And that means that the Arctic will warm even faster in the summer. In the winter, it doesn't matter whether there's ice or not in a way from that point of view, because there's no light to be absorbed. So in the winter, there are other things that come into play.